Dear students, today we'll see what do we mean by Colpitts oscillator. Now here we have today's topic as Colpitts oscillator, and here we have written specifically that this oscillator circuit what we are going to study today is using BJT, that is bijunction transistor or bipolar junction transistor. This we are saying because we can also build up this oscillator using op amps also. Now here, first we will see our definition of Colpitts oscillator, that is an introduction, and then we'll go to see the circuit diagram of Colpitts oscillator. Now here if you see the definition or the introduction to this oscillator says that the Colpitts oscillator design uses two center tap capacitors. So here what do we mean by two center tap capacitor is there will be a capacitor like this and then one more capacitor like this, and here you can have your ground point. Okay, so here this can be taken as your C1 and this can be taken as your C2, and we say that the capacitances are connected in series, so the equivalent capacitance will be C equivalent, that is 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2. So here you can have your C equivalent as C1 into C2 upon C1 plus C2. This is what will be a center tap capacitor means. Okay, now this we are speaking because along with this arrangement of C1 and C2 we will be having an inductor L here in parallel with that combination, and this will be your tank circuit. This will be your parallel resonance circuit, which will be used as a feedback circuit in Colpitts oscillator to have sinusoidal oscillations. Now this point we are going to speak in this introduction in the definition, and this point will be clear to you once we see the circuit of Colpitts oscillator. So here again, if you read the definition, the Colpitts oscillator design uses two center tapped capacitors. So it is simple. C1 and C2 you are putting in series with a parallel inductor L to form a resonance tank circuit. So it is a tank circuit. Basically, we have studied what was tank circuit when you connect a capacitor in parallel with the inductor like this. So we have seen this tank circuit, and this tank circuit when it is energized it is going to produce oscillations. So this is capacitor, this is inductor, it is going to produce oscillations, and the frequency of oscillation is given as 1 by 2 pi root LC. So similar thing here also, this tank circuit we are going to use in Colpitts oscillator, and here also we'll have our frequency of oscillations as 1 by 2 pi root L. Instead of C, we'll be having C equivalent, which will be a series combination of C1 and C2. So here, if you see this introduction, the Colpitts oscillator design uses two center tap capacitors in series with a parallel inductor to form its resonance tank circuit to produce sinusoidal oscillations. So oscillations means you're going to produce repetitive waveforms. So say like this, you're going to produce this sinusoidal oscillations. So it is an oscillator circuit. So basically it will be an amplifier with positive feedback, which will work as an oscillator. Then we'll go to see the circuit diagram. So here if you see the circuit diagram, so the main active element what we are going to use in the circuit will be this a transistor. Now this a transistor will have its emitter terminal here, base terminal here, and collector terminal here. This is your BJT, bijunction transistor. And now here you can see same like your RC coupled amplifier will be having a DC voltage supply, that is plus VCC, which is given to the combination of R1 and R2, that is voltage divider bias circuit. So here this VCC will produce a current to flow through R1, and the same current will also flow through R2. Okay, now this current will develop a voltage across R1, and this voltage you can just name it as VR1. It will also develop a voltage across R2 that will be named as say VR2. Now these voltages will see that the transistor is operating in active region, that is base emitter junction. This junction is forward biased, and base collector junction, this junction is reverse bias, so that the a transistor is acting in active region. It is working in active mode. We don't want here the transistor to work in saturation or cutoff mode. We want to use the transistor as an amplifier, and to use the a transistor as an amplifier, it should work in active region. Okay, so that purpose is solved by this voltage divider, that is a resistor divider network, R1 and R2, that is the voltage divider biasing network. And here you are having a radio frequency coil in the collector region of the transistor, so that it produces very high impedance. It gives a high resistance for AC supply, and it will pass your DC supply. And then we have a capacitor CC here, and input we are having a capacitor CB. So both these capacitors see that the AC is passed and DC is blocked. And then we have in the emitter section of the transistor a resistance RE and CE, which are used for stabilizing the network. Now here, the output of this circuit is taken here. This is the output of the circuit. Now that output is taken here as the input to a feedback circuit. The feedback circuit is a tank circuit. So this is your feedback circuit, which is a tank circuit. Now in this tank circuit, you can see the capacitors C1 and C2 with a ground point in between. So these are splitted C1 and C2 with a inductor L in parallel to their combination. So this is your tank circuit. This is your feedback circuit. Okay, this is your feedback circuit. So here, when the circuit is powered on, okay, when the circuit is made on, when the circuit is powered on, the capacitor C1 and C2 are charged. So here, this capacitors C2 and C1 are charged. Okay. Now this charged a capacitor. Okay. This charged capacitors will have a circulating tank current I flowing through them. Okay. So here you will be having a circulating tank current which is flowing. Now this will be your tank current which is flowing in this. This is your current I which is flowing through this tank circuit. Now this current which is flowing through both C1 and C2 will set up oscillations of frequency F naught. Now this is a parallel resonance circuit. So here you can see the combination of C1 and C2 will be your C equivalent. This will be your C equivalent, and then you will be having an inductor here L. This will become a tank circuit. This will produce oscillations, and that oscillations will be given as frequency of oscillation 1 upon 2 pi under root the value of inductor L and the value of equivalent capacitor, that is when C1 and C2 are in series, then equivalent capacitance C equivalent you will get. C equivalent is equal to C1 into C2 upon C1 plus C2. Okay, so that will give you the frequency of oscillations. Now here, whatever output voltage you get for this circuit, that output voltage will come across the capacitor C2 here. The output voltage will come here. Now this output voltage will come here, and similarly, as the current is flowing through both and both the capacitors are charged, you will have a voltage develop across C1, which will be your feedback voltage Vf. Now this feedback voltage Vf will be given to the input here, that is to the base of the transistor. And once it is given to the base of the transistor, whatever output you get at the collector, this will have a phase difference of 180 degree, because it is the property of the transistor. Whatever input you give at the base will be in phase reversal at the output collector. Now this 180 degree phase shift is there in this loop. And then here if you see, that is here we have made one point as point number 2, point number 3, and point number 1. So if you see the voltage across C2 and if you see the voltage across C1, both will be having a reverse polarity, and there we say that the tank circuit is going to produce another phase shift of 180 degree. So this tank circuit is going to produce a phase shift of 180 degree. So here you have 180 degree phase shift. So the a transistor phase shift of 180 degree and this phase shift of another 180 degree by the feedback network. That is the total phase shift will be 360 degree, which can be taken as 0 degree. And because it is a positive feedback, it is going to help the input, and because it is going to aid the input, the oscillations will take place at the output of this amplifier circuit because of this positive feedback. And this is the basic criteria of your oscillator circuit, which comes under your Barkhausen criteria. Clear? Now here as a whole, whenever you see an oscillator circuit, there will be no specific input to it. Whatever feedback circuit you have, the output of that feedback circuit will be connected to the input of the amplifier. Okay, and this circuit will be initially powered on, and the capacitors will get charged C1 and C2, and there will be a circulating current flowing through the tank circuit. So this is the explanation of Colpitts oscillator. Okay. Now for this explanation, we can write a theory which can go as follows. A construction, if you see, the resistors R1, R2, and RE provide necessary bias condition for the circuit. A capacitor CE provides AC ground, thereby providing any signal degeneration. This also provides temperature stabilization. Then a capacitor CC and CB are used to block DC and to provide AC. The radio frequency choke, that is RFC, which is put in the collector region of the transistor, offers very high impedance to high frequency currents, which means it shorts for DC, that it means it will pass DC, and opens for AC, that means it will block AC. Hence, it provides DC load for collector and keeps AC currents out of DC supply source. Then if you speak about the tank circuit, the frequency determining network, this is a circuit which is going to determine the frequency of oscillations. It is a parallel resonance circuit which consists of variable capacitors C1 and C2 along with an inductor L. The junction of C1 and C2 are earthed, that is, they are ground. The capacitor C1 has its one end connected to base via CC and the other to emitter via CE. This you can explain by seeing the circuit. The voltage developed across C1 provides the regenerative feedback required for the sustained oscillations. Then working of a Colpitts oscillator, when a collector supply is given, transient current is produced in the oscillatory tank circuit. The oscillatory tank circuit current in this tank circuit produces AC voltage across C1, which are applied to the base emitter junction and appear in the amplified form in the collector circuit and supply losses to the tank circuit. If a terminal 1 is at positive potential with respect to terminal 3 at any instant, then terminal 2 will be at negative potential with respect to terminal 3 at that instant because terminal 3 is grounded. Now, this explanation means that the feedback circuit is going to produce a phase shift of 180 degree. Therefore, in the last line, we say that therefore points 1 and 2 are out of phase by 180 degree. So here a phase shift of 180 degrees produced by the feedback circuit, and that 180 degree, if you add with the phase shift of the a transistor of another 180 degree, the total phase shift of the loop will be 360 degree. And this is the basic criteria that you are providing a positive feedback to the amplifier. This is the basic criteria what we studied in Barkhausen criteria for an oscillator circuit. So as the common emitter configuration transistor provides 180 degree phase shift, it makes 360 degree phase shift between the input and output voltages. Hence, feedback is properly phased to produce continuous undamped oscillations. When the loop gain, that is beta into the A of the amplifier is greater than 1, the oscillations are sustained in the circuit. Okay, so here the beta is the gain of the feedback circuit and A is the gain of the amplifier. Then if you go to see frequency of oscillations, the equation for frequency of oscillations for Colpitts circuit, that is a Colpitts oscillator, is given as F R, that is resonant frequency, is equal to 1 by 2 pi root L CT. So this we can also denote it as frequency of oscillations. F naught is equal to 1 upon 2 pi under root L C equivalent, where C equivalent is the effective capacitance, equivalent capacitance of a capacitor C1 and C2 where C equivalent can be given as C1 into C2 upon C1 plus C2. Okay, so this will be the formula for frequency of oscillation, which can also be called as a resonant frequency of the parallel resonance circuit. So it can be also denoted as FR or F naught. It is given as 1 by 2 pi under root L, that is inductor value, multiplied by the equivalent capacitance value of both the capacitances C1 and C2. Then where CT is the capacitance of C1 and C2 connected in series, and it is given as 1 upon CT is equal to 1 upon C1 plus 1 upon C2. Here you can see, or it can also be given as CT is equal to C1 into C2 upon C1 plus C2. This is the simple formula when capacitors are connected in series. Then if you go to see the advantages of Colpitts oscillator, here we have mentioned few advantages. A Colpitts oscillator can generate sinusoidal signals of very high frequencies. It can withstand high and low temperatures. The frequency stability is high. Frequency can be varied by using both the variable capacitors. Less number of components are sufficient. The amplitude of the output remains constant over a fixed frequency range. Then if you go to see the applications of Colpitts oscillator, so here we have mentioned few applications. Colpitts oscillator can be used as high frequency sine wave generator. This can be used as a temperature sensor with some associated circuitry, mostly used as a local oscillator in radio receivers. It is also used as radio frequency oscillator. It is also used in mobile applications. It has got many other commercial applications. Thank you, students.